okay? So this is 12 reds. So it takes 12 of these to make one of those. So that means that this fraction would be 12 out of 12, if I'm talking about the number of reds. This one would be 11 twelfths. This one would be 10 twelfths. And then 9 twelfths, 8 twelfths, 7 twelfths, 6 twelfths, 5 twelfths, 4 twelfths, 3 twelfths, 2 twelfths, and 1 twelfth. So this red one is 1/12 of the gray one. And then it steps up beyond that. So now we can do some pretty cool stuff with this, now that we understand that. So if I want to find out what's equal to 1, and I say, okay, well, let's say I've got a blue one, and then what else do we think would fit in there? Well, it looks like maybe it's this yellow one right here. So I add those, I put those together in the same line, and I see that I have the light blue one is 9 twelfths. So this is 9 twelfths, and then I added to that the yellow one, which was 3 twelfths. And I just did my first addition of fraction problems, 9 twelfths plus 3 twelfths. All right, so then we want to try another one. And we'd say, okay, how many of these? So that one and that one look like they fit. So here, the fuchsia one is 6 twelfths, 6 twelfths plus 6 twelfths. And so 6 twelfths plus 6 twelfths equals 12 twelfths. And you could just, do a bunch of these, if I do another one down here, that's light blue and green, is that going to be equal to a 12th? Let me see. Yep, it is. So the purple, or what's that, lavender is 7 twelfths. And plus the green is 5 twelfths. So 7 twelfths plus 5 twelfths. So what you're doing here for your students is you are reinforcing that they need to always equal the length of this one here. That's the one. That's the whole that we're talking about. And it doesn't even have to be 2 colors. Maybe it's 3 colors. Let's see if I could do one with 3 colors. So I've got, I'll do purple again. Maybe purple. And then orange. And then 2 reds would do it, I believe. Like that. Okay. So here I would have purple is 8 twelfths. And then orange is 2 twelfths. And then plus 1 twelfth and 1 twelfth. So there's really no limit to what you can have them do here well, I guess there's a limit, but there's a bunch of different ways that they can do it. And you can have them build whatever you want. And okay, so keep that in mind, because I'm going to erase some of this stuff. And if you want to pause it right now, that's a good time to. I'm going to erase some of it, and when I come back, we're gonna do some other stuff with this manipulative. Okay, so what I've set up here is those are the ones that we just built a second ago that we all knew added up to 12 twelfths. And then down here on the side, I've written all of the fraction equivalent for each color. And then if I could simplify it, I did. So I have 5/6 and 3/4 and 2/3, that sort of thing. And then we're going to take a look at some of those. Okay, so if I want to do one more here, just to kind of reiterate what we're doing. So I know that my goal is to make this be the exact same length as my top color. So the single color at the top, so that gray one at the top. So then what I have here, this is 10 twelfths plus, and the orange one is 2 twelfths. And that equals 12 twelfths. And what I can start to notice, or start to explain to students, is that we also call the 10 twelfths, we call that 5/6 and then we call the 2/12 1/6, and they're the same size pieces, so I can add them together, and so then I get 6/6, which is equal to 12/12. So we start to show them the algorithm that goes along with this, all right? Now, what if it doesn't equal a whole, like this one, 12 over 12? What if it equals this one, which is the brown one, which is 11/12? So, okay, so what I'm trying to figure out here is what colors add to give me 11/12? Well, I know that a fuchsia one and a green one will add up to be that exact same length. Okay, so no problem. So all I have to do is figure out that the fuchsia one is 6/12 and the green one is 5/12. And so 6/12 plus 5/12 is equal to 11/12, which is what this one is. And I also see that 6/12 could be written as 1/2 plus 5/12. Now this is where it starts to get a little bit weird for students, because I no longer here, at least I had the same denominator. Whoa, what the heck? These are not even close. So what do I do with my denominators? And we can go back and we can emphasize right here, I was able to add the 6 plus the 5 because I had the same size pieces as my denominator. They're all 12ths. Here, I don't have the same denominator, so I need to turn these into the same denominators in order for me to add them together. By the way, I'm correcting something that I did wrong right there. This little slanted fraction line, I never use unless it's a final answer. When I do my actual problem or my work, I always use the horizontal fraction because I want my students to see numerator versus denominator. I don't want that slanted line because that gets super confusing for them. So I'm going to write it a little lower because I didn't like that. So this is 1/2 plus 5/12 is equal to, and so this is a little bit trickier for students to see why it would be equal to 12. So what we have to figure out is, all right, so for this fuchsia one, how many of these little 12ths do I need? Well, I need to have 6 of them, and those are 12, so this is equal to 6/12. Okay, we're gonna do one more of those that shows you that you don't always have to equal 12/12. So let's see, we have this one here, and that is 9/12. That's what that one's equal to. And I believe a neon and a green equal 9/12, equal the same length there. So the neon is 1/3 and the green is 5/12. So now what I did was I used the simplified fraction for it. So I used 1/3 for the neon and 5/12. We don't like that. I don't want them to be in different denominators. So what does this equal in 12? So then I see that that equals 4/12. So I could change this to 4/12 plus 5/12 is equal to 9/12. So I'm not saying the word common denominator at all. When I'm doing this, I'm just showing them that in order for me to add them together, I need to know how many this is compared to that denominator. I need to have them the same size pieces so I can add them together. And I look over here at my chart and I can see that the 1/3 is equal to 4/12. So these rods are pretty handy. They're pretty good to use for an introduction of adding fractions and equivalence of fractions. Because they give you a lot of variety of things you can build. You don't always have to build the 12/12. You can build the other fractions. And then we start creating problems that are like 1/3 plus 5/12. What's that equal? Well, it equals 9/12, or we get simplified down to 3/4, but we'll get to that later. Okay, so that's the color rods, right? We're going to take a look at another manipulative here in just a second. Okay. The next, and I think probably the last part for today, because this video is already quite long, is we're going to take a look at what fractions are and how they can be represented. So I have three different ways to represent fractions, okay? So fractions are basically a comparison. That's what they're doing. They're comparing two things to each other. So I have three different ways that could be presented. So the first one here, the very top one, we call this a linear comparison. Okay, so we are comparing the length of this. So what you could say is that the length of this is 3/5 green. Okay, the length is 3/5 green. You also could say that the length is 2/5 green, or blue, excuse me, 2/5 blue. So when you have the whole length of something linearly, then you're comparing how long this part is compared to the total. So the length is 3/5 green, or the length is 2/5 blue. Okay, two ways of doing it. So that'd be a linear fraction. Now this one is called a set fraction. Notice that we're not worried about the linearness of this, although you could organize it and line it up so it is linear. But for this one, you would say something like this. This set is 3, and then 1, 2, 3, 4, 5, 6, 7. 3/7 red. Or you could say it is 2/7 green or yellow. Actually, green and yellow. It's 2/7 green and yellow. All right. You could say it's 1/7 green or 1/7 yellow. You could say it's 2/7 blue. You could say it's 4/7 not red. Okay, so 4/7 not red. All right. So this is the set model, and what you're doing is you're comparing the number of items that you care about to the total number of items that you have. Okay. All right, and then the last one down here actually ends up being usually the most useful, and this is called the area model. So we have the linear model, the set model, and here's the area model. I guess I should put a model on there for each one of those. And here you're comparing the area of something. So you see we have two shapes that we can easily find the area of. That is a rectangle and a circle. So that's why people like to use both of those. And we actually are going to use them as well. So here for this first one, you might say it's half the area is yellow. 1/2 the area is yellow. Okay. Over here, you might say 1/3 of the area is blue. Okay, and of course, lots of other things you could say about it, but that's a couple of different ways. So there are three different ways that you can talk about these things. You have linear model, set model, and area model. We'll be using all three. We probably use the area model the most, but we'll be using all three. Okay, and as is true with a lot of our first days of a new topic, the homework is relatively light because it's a lot of understanding. So I am going to build a few things and have you guys write some set models, area models, linear model expressions. There'll be a few little things for you to do, but today is mostly about understanding different things about area, and we'll really get into the nuts and bolts of adding, subtracting areas on our next video. Okay, I know this video is a little bit long. They won't all be this long, but this takes some time to go through all of the introductory stuff. All right, I will talk to you guys soon.